name is Monica Stockman. I'm with the AISD Steel Solutions Center. It is my pleasure and my honor to introduce Clifford Schwinger. He is the Vice President and Quality Assurance Manager with the Harmon Group. He graduated from Lehigh University, and he has over 30 years of structural engineering experience in building structures. He's been with the Harmon Group for 22 years, and he is a member of the AISD Manuals and Textbooks Committee, so he has plenty of experience in steel building as well. He's also an adjunct instructor at Drexel University in Philadelphia. So without further ado, I will go ahead and turn it over to him, and enjoy.
Okay, thank you, Monica. Can everybody hear me okay in the room? Okay, today I'm going to be talking about quality assurance for structural engineering firms, tips, techniques, and strategies. I believe our company, the Harmon Group, is pretty unique in that we've had a full-time QA manager for over 20 years. I was reading not too long ago that Google hired their first full-time chef when they had only 30 employees. Well, the Harmon Group hired their first full-time QA manager when we had only 7 engineers. So quality assurance has been something that we've been on top of for a long time. What I'm going to focus on today is basically a description of what our quality assurance program is and how it's evolved over 20 years. And before I begin, I just wanted to get an idea of how many structural engineers are in the room who work for firms and are the engineer of record on projects. Okay? And how many other people in here, engineers working for detail connection or fabricators or detailers or contractors, anything else? Okay? Okay, I just wanted to get an idea of who the audience was. Okay, what we're going to be covering today are 2 broad topics. We're going to talk in the first half of my discussion about quality assurance programs, and in the second half of my presentation I'm going to talk about quality assurance reviews, the procedures, tips, and techniques. So what is a quality assurance program? Basically, a QA program for structural engineers is a defined set of procedures and standards used to facilitate design and to facilitate documentation of that design. Basically, what our QA program is, it's a program we have where we try to take everybody's lessons learned and funnel them into a single location so that everybody can learn from the mistakes of others. And as the QA manager, I sometimes tell people the reason I'm the QA manager, my qualifications are I've made more mistakes than most other engineers. Of course, I've been doing it for 30 years. Now, the problem is 30 years ago, if you made a small mistake, and when I say mistake, it could just be missing information on a detail or whatever, things were a lot more forgiving than they are today. Nowadays, if there's anything missing, you start getting RFIs, and it's not long until change orders follow. So things are a lot more adversarial today, and it's more important than it was years ago to get your contract documents up to speed and as near perfect as you can possibly get them. So why are QA programs so important today? Well, everybody's heard of the term fast-track construction. But lately we've been seeing a lot of projects that we're classifying as hyper-track, where things are moving faster and faster, and it's becoming an increasing challenge just to meet those schedules. There's more changes during design, whereas years ago design was a linear process from beginning to end. Now, on a lot of our projects, we're so far ahead of the architects, we'll run with the ball for a while, we'll issue a mill order package, and then we'll have to step back and make a lot of revisions to catch up so that as the architect catches up. And so there's a lot of this, it's a lot more fluid during design. Young engineers are taking on greater responsibility today than they did in the past. Years ago when I started, young engineers spent the first 4 or 5 years of their career pretty much learning the trade and doing manual calculations every day. And they gradually learned the art of structural engineering by osmosis, sitting next to more experienced engineers and designers. Today, with the advent of computers, what would have taken an engineer a year to design by hand can be done in about 20 minutes on a computer. So what's the engineer going to do in the meantime? You know, all those repetitive calculations aren't needed anymore, the manual calculations. So now young engineers are being asked to take on more responsibility in their careers, doing details, coordinating with the architect and contractors, etc. We're using computers for everything these days, and understanding software limitations is important for structural engineers. You're not going to find those limitations in the user's manuals from the software manufacturers. They're not going to tell you what the computer program doesn't do, and usually we have to just find that out gradually by using the programs. Codes are getting increasingly complex. I don't have to tell anybody about that. RFIs and change orders. I was mentioning before about the adversarial relationship that sometimes pops up, usually at the end of projects, not always at the beginning. The lost art of structural drafting. You could take a framing plan that was done 50 years ago, put it in a picture frame, and hang it on your living room wall. You can't do that with drawings produced today. Unless everybody agree with that? Today's drafters have been replaced by CAD operators who can tell you 10 ways to draw a circle, but they can't properly dimension the circle. So our quality assurance program tries to address the lost art of structural drafting. And the last two go hand in hand, the need for engineers to be proactive and to be good communicators. Engineers generally aren't the best communicators, but nowadays with our projects, with steel design being so far ahead of the architectural design, we have to take on a more proactive role and become better communicators and ask for the information we need, because that information is not going to be offered up unless we ask for it. So the advantages of having a QA program are we're going to see better design, better drawings, a more efficient design process. There should be fewer mistakes on our contract documents, fewer RFIs and change orders, and since we're all in business to make a living, earn a living, increase profits, hopefully. Now, before I talk about our QA program, I just wanted to point out two publications that everybody in this room should have a copy of. The first one is this case document 962D, a guideline addressing coordination and completeness of structural construction documents. This came out a couple of years ago, and basically this could serve as a template for producing a quality assurance program. It basically addresses the reasons why structural construction documents have suffered in quality over the last few years and what can be done to turn it around. The second publication I recommend is The Contractor's Guide to Change Orders. When I came across this book a couple of years ago, I felt as if I was a football coach who stumbled upon the other team's playbook. This publication basically tells contractors how to mine a set of contract documents for change orders. So I read the book, and I just made sure if they said, look for this, I made sure our drawings didn't have that flaw. So I highly recommend both of these publications. This is a little bit more entertaining reading, only because you can feel the pain as you read that and realize that, geez, that contractor has this book. Okay, 20 years ago when we started our QA program, it was comprised pretty much of a QA manager who was in the office 8 hours a day and available to answer questions. And before our projects went out for bid, he did a single QA review and reviewed the drawings for mistakes and for completeness. But because of fast-track scheduling, that process doesn't work anymore. So now we're going to talk about what is a modern day, what are the requirements of a modern day quality assurance program? Our QA program is comprised of 6 components right here, and this is pretty much a fundamental slide. If you take away nothing else from this presentation, this is what goes into our quality assurance program. We have training for our young engineers. We have a set of design standards, CAD standards, a project delivery system, a knowledge base, and involvement of the QA manager and QA reviews. So I'm going to talk a little bit about each of these. Okay, the training for young engineers. As we were as I was saying before, the learning curve has been greatly compressed for young engineers entering the profession. So what we've adopted is a series of weekly formal lunchtime training seminars on a variety of topics that engineers need to be proficient at in order to be productive. And the list of topics, I guess everybody in this room, you can come up with your own list, but the list is endless. Some of the topics we've talked about and given seminars are on connection design, slabs on metal deck, and you can see the list. The connection design is something you could spend months giving lunchtime seminars just on that one topic. But other topics, like for instance window washing davits. How many engineers learn about window washing davits in college? Nobody. But window washing davits have been a thorn in my side for about 30 years. It's a little thing that if you don't pay attention to, it can come back and bite you at the end of the job when you find out that the architect wants to put a window washing davit on top of a W12 by 19 beam. It just isn't going to work. So we try to be proactive and teach our young engineers about window washing davits and all of these other things before they need to know that information. Design standards. We have in-house design guides, office standards, and checklists for everything, for all topics related to structural engineering. And the purpose of that is there's more than one way to design a building. With steel design, you can either use ASD design or you can use LRFD design. Each one is perfectly acceptable, and there's no problems unless you're working on a project and one engineer is putting service load reactions on the drawing and another engineer is putting factored reactions on the drawing. That could be a problem. So in order to get everybody on the same page, you have to have office standards. Checklists are invaluable. Checklists serve as a roadmap of sorts to help engineers go through something they've never done before. If, for instance, window washing davits. I'm using that as an example again. What do you have to know about window washing davits? Where are the typical details? How do you design them? What are the loads? And the list goes on. The list is basically endless. And our quality assurance program is an ongoing work in progress, and it'll never be complete. As we come up with new things, we add things to them. Drafting and CAD standards. I was talking before about the lost art of structural drafting. And our CAD standards, drafting and CAD standards, try to address that problem. We have standardized drafting procedures, checklists, typical details, go-by drawings, and standard blocks. The big thing on this list is the go-by drawings. We have go-by drawings for every possible type of framing plan there is, both steel and concrete. But our structural steel framing plan, for instance, has every possible combination and permutation of anything that can happen on a steel-framed floor. We have plate girders, trusses, sloping columns. We have hangers, suspended pits, elevators, escalators, window washing davits. We have moment connections, drag struts. Anything that you can possibly think of that can happen on a steel framing plan, we put on our go-by framing plan. And the purpose of that is that quite often in the past, a young engineer would just be given the last steel job and say, here, follow this. But that doesn't always work, because what if the last job didn't have an escalator in it or didn't have plate girders? And so what we do, we try to address that with go-by framing plans. And if our framing plan is missing something, if somebody says, well, you don't have a whatever, we'll add it to it. And the other advantage of go-by framing plans is they prevent a gradual divergence in standards. As companies get bigger and you start opening up multiple offices, you can gradually see changes in the different offices. There can be a divergence, and this is an attempt to address that and prevent that from happening. Our project delivery system. We have a project delivery system. It's basically a series of checklists and procedures that help take engineers from the beginning of a project through the end of the project. And this is the roadmap. This is the roadmap that they follow. At the beginning of a project, in this project startup folder, there are checklists telling the engineer what they have to do at the beginning of the project. One of the things is to fill out a design criteria form. The design criteria form has all of the loads, design standards, the fire ratings, everything related to wind and seismic. That design criteria form is filled out and it's updated as more information becomes available. And it's basically there for everyone to see who's working on the project in the project notebook, so that there's never any question about what the design standards are for that particular project. The engineer then is told to set up a meeting with the project manager and the quality assurance manager, and we go over the project and how they intend to frame it and all the little details. And we talk about various structural systems and the optimal way of framing the steel framing, if it's a steel building, etc. Then you carry the project through, and when you get to construction administration, we have checklists for structural steel shop drawing review, checklists to tell the engineer everything they have to check when reviewing a steel shop drawing. We have meeting agenda templates for when we have our meeting with the steel detailer, the pre-steel detailing meeting, the pre-concrete meeting, the meeting with the inspectors. So basically everything an engineer needs to take a project from beginning to end is in this project delivery system. We have a knowledge base. A knowledge base is a server-based database of knowledge related to structural engineering, and it's similar to Wikipedia. In fact, it looks exactly like Wikipedia. You just type in a search phrase and you can find out anything you want to know about whatever. The cost of structural steel, window washing davits. We have checklists on designing base plates. I think our checklist for base plate design has about 60 items in it, and this is an invaluable resource. Engineers today, especially the younger engineers, like going to the computer and using the computer to find this information, and this is an ideal way of getting all of our information into a single place. All of our design guides, seminar notes from the design engineer training seminars, everything is in the knowledge base. So it's a single place to go. And it contains knowledge, not just information. For instance, it's not just facts, it's what did we learn from those facts. For instance, in the case of sometimes when we build buildings on soil that has high sulfate concentrations, we need to use type 2 cement. Well, what is type 2 cement? What's the availability of type 2 cement? What is it about sulfates that actually does something bad to the concrete? And how does type 2 cement prevent that from happening? And what if you can't get type 2 cement? What can you do instead? Well, you can use slag. Well, that's knowledge when you take all of those lessons learned and facts and put them in an easy-to-understand narrative. It explains what could be a difficult topic and puts it into perspective. And finally, the sixth component is involvement of the QA manager, establishing and maintaining design and drafting standards, answering technical questions, staff training, performing QA reviews, and reviewing the framing plans and details before they go to CAD. I want to see the details before our CAD department spends a lot of time drawing them up. I don't want to get 5 sheets of details and bleed all over every detail. That's demoralizing to me. It's demoralizing to the engineer who did the details. And the CAD guys are going to be grumbling. So it's better to work through all of the problems with details before they're drawn up. And that also provides valuable one-on-one training between myself or another senior engineer who might be helping out and the engineers who are coming up with these details. One of the important factors or keys to quality assurance is that it be ongoing. It's not enough just to get a set of drawings thrown on your desk at the end of a job. QA has to be an ongoing process, and it requires the QA manager to maintain some level of familiarity with all the projects as they progress through design. It's more or less a proactive approach to catching problems early before they become problems that are difficult to fix. And ongoing QA is basically the key to enhancing efficiency and productivity and to squeezing as much as we can out of the QA process. So that was a summary of our QA program. Now I'm going to talk about the quality assurance review strategies and tactics. QA reviews are in-house reviews conducted to verify that our design and documentation is in conformance with the procedures and practices mandated by the QA program. There are two primary purposes. As structural engineers, we all know that redundancy is good, right? As the QA manager, I'm not the primary load-carrying member of the design. The primary responsibility to get that design right falls on the design team in our office who's working on that project. But the QA manager provides a second set of eyes in order to catch mistakes that may have slipped through the cracks. And the second purpose of the QA review is to monitor the effectiveness of the QA program. If I continue to see a certain problem slipping through on job after job after job, that's a sign that something isn't right with the QA program, that something has to be fixed. We had this problem a couple of years ago with the seismic response coefficient for steel structures. You want to, in areas of low seismicity where most of our work is done, you want to use an R factor of 3. But I was seeing 3.5, 6, because a lot of engineers would figure, well, if 3 is good, then 6 is even better, not realizing that they were putting a lot of cost into the connections. And also, since we design our own connections, they didn't even know what was involved in designing a connection when you had an R factor of 6. So it was that unknown about what exactly the seismic response coefficient was doing and why they should use an R factor of 3 that led us to continue to add information to the QA into the knowledge base, and we gave some seismic seminars just to try to drive home that point. Like I said before, a single QA review at the end of design doesn't work anymore. And today with fast-track projects, we have to do multiple QA reviews. On large projects, I'll do as many as 12 QA reviews. The first one will usually be when the foundations go out. If it's pile foundations, there'll be a pile foundation QA review. Then there'll be a steel mill order QA review, and so forth and so on. And like I said, on smaller projects, it might only be 3. On large projects, it could be 12. Now, there are 2 overriding goals when performing a QA review. The primary strategic goal is to verify that the structure is properly designed. And not to oversimplify it, but it's basically the primary goal is to make sure the building doesn't fall down. So that involves looking at the big picture, load paths, member sizes, and critical connection details. The secondary strategic goal, in simple terms, is to make sure we don't get sued. In other words, to make sure that our construction documents are complete, coordinated, and correct. We want to look at the drawings through the eyes of everyone that's going to be using them. Is the contractor going to be able to understand our drawings and be able to get all of the information off the drawings that they need to build the structure? Is the detailer going to be able to get all of the moments, reactions, shears, member sizes, and have all of the dimensions? Is the inspector and building official, are they going to be able to understand our design intent? And the engineer performing a peer review, is he going to be able to understand our drawings? Are they going to be complete and correct? And likewise for the engineer shooting spitballs at our design. The young engineer reviewing shop drawings, this is an important one, because if that young engineer can't decipher what's on our drawings and can't clearly understand what is on the structural drawings, the likelihood of them finding a mistake that may have slipped through the detailer is going to be greatly diminished. And if our drawings are complete, correct, and coordinated, the chances are that the detailer isn't going to have many mistakes, on the shop drawings, and so this young engineer is going to have a much easier time of reviewing the shop drawings. And finally, if something goes wrong, what is the legal profession going to say about the quality of our construction documents? So these are the tactics that are used when we perform QA reviews, and I'm sure anybody who has reviewed a set of drawings before, you can probably add to this list. But generally, you look at the big picture, verify load paths, etc., and I'm going to go into each of these a little bit in depth. Looking at the big picture, Engineers who work on projects every day can sometimes lose sight of the big picture. And someone with a fresh set of eyes on the structure can sometimes see things that are going to pop out that weren't apparent to somebody who's working on the job every day. Load paths, problems with connections, inefficient framing, the wrong loads being used, missing loads, problems with the computer model. The big thing here, I was reviewing a model a couple of years ago, and the engineer had the switch turned on the computer that generated the self-weight of the structure. But they thought that switch was turned off, and they put the self-weight of the structure in manually, so they had the self-weight in twice. So our foundations were a lot heavier. Everything was heavier. And that's better than the other way around if they had the dead load turned off and only had the live load in. Problems with the R factor. I discussed that before. That's something I think we finally got that figured out in our office. And missing or improper expansion joint layouts. Load path issues. Are there any unrealistic load paths? Are there any loads jumping in and out of shear walls or braced frames, or any unrealistically rigid diaphragms? Here's some examples. I know most people in this room probably figure this is too elementary to even be worth mentioning, but I know there have been some real problems when engineers have failed to consider the horizontal reactions at the top and bottom of sloping columns. Everything has to resolve out. And it's not enough just to consider what happens here and to design that member. You then have to follow it to see how this reaction and that reaction eventually meet up again. Usually they're going to just cancel out via a braced frame or shear wall, or an opposing sloping column that might be on the other side. We did a job several years ago. It was a parking structure about 300 feet long, and we modeled it. It was a computer model, and it was modeled with a rigid diaphragm, and it was pretty torsionally stiff. We had shear walls on three sides and a moment frame on one side. So the computer said that 95% of the lateral load went into this shear wall. But I don't know about you, but we weren't comfortable with this. We're never going to put less than the tributary load on assist one of the brace frames or moment frames in the lateral load resisting system. So what we did and what we do, and this happens on every job, I guess we made this 50%, and we probably made this something like 75%. We enveloped it. We didn't want to just make this 50% because this diaphragm does have some rigidity, and this is going to take more than 50%. But it's not going to take 95%. And add to that the fact that in this particular case, this was a precast concrete parking structure. The floor diaphragm wouldn't have been able to get that 95% of the shear into that shear wall anyhow. This is another problem that we see on most of our jobs. When we input rigid diaphragms, we'll follow the loads down on a braced frame, 75 kips, 100 kips, and all of a sudden 50 kips. Usually loads get bigger. They definitely get bigger when you have a flexible diaphragm, but when you put in a rigid diaphragm into a computer model, you're going to see things like this happen. And what causes this is there was probably a stiffer braced frame a couple of bays away that was drawing load out of this brace frame via that rigid diaphragm. So this is something, again, we address this. We're not going to leave that like that. We're going to make sure this brace frame can take its tributary load. Here's another one. In this case, we have a braced frame where, for whatever reason, it had to shift over a couple of bays on the lower level. So you look at the computer model, and down here, you see a W12 by 19 or a W14 by 22 on the framing plan. And that's because in the computer model, there's an infinitely rigid diaphragm, and the computer says that all that load is going to just get sucked out of this brace frame and shoot over here through that 6.5-inch slab or whatever it is. It's going to completely ignore this drag strut. So again, this is one of the, it seems that limitations on computer software are one of the big things that I spend my time searching for problems on and finding problems on. So what we need here is we need a drag strut that's good for 150 kips or whatever. We need drag strut connections, and because we need a clear load path from that one brace frame to the other. Check the framing. Somebody asked me once before, you mean to tell me you check every single beam and reaction on all of the framing plans? And the answer is yes, but it's how I do it that saves time. With computers, you could model 10,000 tons of steel in a couple of hours, but when those drawings are handed to me, I'm looking at them by hand. And so in order to do that, what I do is I review the typical beam, typical girder, and a typical column in order to verify that all the loads and all of the design constraints that are in that model are correct. If my manual calculations give me a beam design and a girder design and a column design that are identical to what the model has produced, then I can have a pretty high level of comfort that the rest of the framing was designed correctly. Now, I'll still look at all of the member sizes. If the typical beam was an 1835 and the typical reaction was 45 kips, then shorter spans with the same trib should have smaller sizes and smaller reactions. So you generally just get a feel looking through all the framing. Once you know what the typical beam, girder, and column are, you get a feel for what those reactions and member sizes should be in the rest of the floor. I do review all of the major load-carrying members, plate girders, transfer girders, trusses. I don't give those short shrift. They get a careful examination, and any unusual connections, any heavy connections, they get looked at closely. Wind and seismic loads, I do quick manual calculations. With the complex codes we have today, what I do is I just calculate the wind pressure at the base of a building, the wind pressure at the roof. I calculate the average wind pressure and multiply it by the sail area of the building to get my base shear. And then I'll split it up into however I think it should be distributed among the brace frames. I look at the brace frame elevations, and more often than not, my forces that I calculated in 5 or 10 minutes are pretty close to what's on the brace frame elevations, and if they're not, I ask why not. And it's sometimes I wonder, with wind tunnel studies and all these complex code equations and 100 different load combinations, at the end of the day, if you use that quick shortcut method, that's a quick way of usually getting a pretty close design to what you need. Same thing with seismic loads. The only thing you can't easily do when computing seismic loads is get the exact building period. So that's what I have to sort of hang my hat on when I'm calculating my seismic base shear. I'll use the approximate period, and I'll compare it to the exact period that was used by the engineers doing the design. And if it's usually, I think there's an upper limit on what the exact period can be. It's the approximate period by whatever that coefficient is. And as long as everything is in sync, then I have a high level of certainty that exact period is probably accurate. And again, check unique framing, not in the computer model. I'll talk about that in a second. But first, I want to talk about the reason that we want reactions shown on the framing plans. For 20 years, we've always been proponents of showing reactions on the framing plans because AISC has been telling us to do that for 20 years because it increases the economy of structural steel buildings by allowing fabricators to detail connections for the actual reactions, not some fictitious percentage of the uniform load capacity of the member. So we've been doing it for that reason, but more so when you show reactions on the framing plan, it basically makes QA reviews a whole lot easier because load paths are easier to follow. Mistakes are easier to find, and by showing the reactions on the plan, you can see how hard the members are working. If you just look at a framing plan, and I've done this because sometimes we'll do peer reviews, and when I look at set of framing plans and there's no reactions, I just don't have the same feel for how hard that structure is working as I do when I see the reactions. And again, when you see the reactions, it forces the designers to think about the connections. If you see a 300 kip reaction on an 18 by 35, well, obviously that's a mistake because that's probably beyond the shear capacity of an 1835, but mistakes just jump out of the page a lot easier when reactions are provided. And then finally, of course, it does reduce the structure cost by allowing the fabricator to detail the connections for the actual loads. When we do projects, especially the fast track projects, we send drawings out, we send a mill order package out. And usually when that mill order package goes out, a lot of this information isn't known. So all of these blanks have to be filled in before the job is done. And a lot of this stuff can easily be missed. Things like elevators, escalators, once again, davits, window washing davits, stairs, hangers, theater rigging, folding partitions, mechanical loads, be they rooftop equipment loads or heavy hung piping, horizontal loads from rigging in theaters and ballrooms, catwalks and expansion joints. These are things that generally you're not going to see. Some of this stuff you can model in your computer program, but you're not going to model davits in the computer program. And I don't know anybody who models horizontal rigging loads in their analysis, in their floor framing analysis. Because usually that stuff isn't known until the very end of the job anyhow, till the very end of design. We check critical connections, unusual connections, connections with complex geometry, or connections with large reactions. This is something I saw not too long ago. This is a really strange framing plan. I'm only zeroing in on a very small area, but basically we had this was a W40 by 593 framing into another W40 by 593. These were huge loads. There was some sort of an artificial lagoon built on top of this floor. And the architect had certain constraints as to what they wanted the framing to look like on this side of this skewed beam. So I was looking at this, and I quickly realized there's no way you're going to be able to detail a connection. This connection is virtually impossible to detail. It's too steep of a skew and too large of a reaction. And that's one of the problems with computers. You can do this and you can do whatever you want. You can have that beam coming in at a 2-degree angle if you want on a computer. You could have 12 beams framing into a column on the computer, but when it comes to detailing those connections, it's going to be very difficult. So we had to reconfigure this to make it constructible. And this is something we've all seen when you have roof joists. There's always going to be some W shapes up on that roof, and if those W shapes are not deep enough, you're going to wind up with some unusual connections. So we want to make sure in the case of an LH series joist that we have at least a W14 framing into the girder so that we get 2 rows of bolts. Look for mistakes. Wrong reactions, members too small, improper framing configurations, missing sections and details. The list is endless. Here's one. We had a column with some beams and girders framing into it, and right before the drawings went out, we got some revised architectural drawings, and there was an opening that was thrown in there at the last minute. So we had to quickly move that girder off the column line, and it was framed into this beam, but the beam wasn't revised, and worse than that, I mean, the beam may have been able to take the moment, but now all of a sudden the reaction, instead of being 36 kips, was 100 kips. That would have been a serious overstress. Look for subtleties. Subtleties include things that aren't apparent at first glance, like column splices at inappropriate locations. If you have a column splice, typically column splices occur 4 feet above a floor, but usually the floor is bracing the column, but on occasion, if you have a small mezzanine, that floor is not bracing that column. So if a splice is occurring 4 feet above a floor that's not bracing the column, you've basically got a splice at the mid-height of a column that's twice as high as you think it is. And that's something we've seen before. Expansion joints that are not properly configured and they wind up locking up the structure. Floor diaphragms that lack strength and stiffness. Here's an expansion joint problem. We had a building a couple of years ago. It was a long building with an expansion joint right down the middle, but for one reason or another we had to jog the joint for architectural reasons. Now when we detailed the joint, we detailed them to permit movement only in one direction. So when the joint turned 90 degrees, we had a sliding joint here, but it was only allowing slip this way. So basically we locked the two halves of the building together. So our solution was to redetail that connection so it would allow movement in this direction. This is a problem that occurred a couple of years ago. It was a theater we were doing. We had this was the stage and this was the main seating area, and there were balconies along either side of the theater. We had a rigid diaphragm modeled in the computer, and the computer was telling us that these columns, which were about 80 feet high, had to be W12 by 65s. But unfortunately, our floor diaphragm wasn't strong enough to brace those columns. It wasn't as clean as what you see here. There was a lot of zigzags back and forth. And in reality, these columns had to be W14 by 211s. So that was a case where we would have had a serious overstress in the columns had we relied on the computer's answer by naively putting in that rigid diaphragm and relying on it. Look at the drawings through the eyes of others. Is everything shown on the framing plans that will allow the contractor to build the structure without having to second guess or issue RFIs? Is every linear foot of the building covered by a section or detail? Is everything clearly indicated? I tell the engineers to take off their engineering hats when they look at the drawings and look at the drawings through the eyes of somebody who's not an engineer. Because basically our contract documents are really they're basically directions on building the building. They're no different than the instructions you read when you're trying to put together a bicycle for your kid. And this is just a 50,000-ton bicycle. And so if your directions are not well thought out, the structure may not be built the way you anticipated. Review for clarity and consistency. Look for conflicts between the framing plans and the sections or details. Inconsistencies with the framing, group similar beams. And I tell her, we're a big proponent of the use of dittos. A long time ago when drawings were done by hand, if you had a long string of beams, you would have an 1835 at this end, and you'd have a string of dittos and an 1835 at this end. Nowadays with computers, you don't get that. And so you could get some small subtleties. You could get 18 by 35s with 3/4 inch camber, 1 inch camber, a 35 kip reaction, a 37 kip reaction. And what we do is we just try to envelope it. And I've actually talked to several fabricators over the years, and they said that when they see dittos, that could actually lower the cost per ton of steel by basically clean, simple drawings are basically a form of psychological warfare, again, with fabricators to lower the cost per ton of your structure. Look for omissions. Missing things are always the hardest to find, and they could be missing reactions, sections, details, dimensions, elevations, member sizes, reinforcing steel, even missing members. In a steel-framed office building, typically you're going to have beams at maybe 10 or 12 feet on center, but it's not unusual that for one reason or another you might have a spacing between two beams of 15 or 16 feet. It's not going to jump out, but you're usually going to have to add another beam in there. Look for the little things like spelling mistakes, and these are actual mistakes I've seen on the drawings. And look for one time I saw one sentence that had 5 spelling mistakes, including schedule, moment, and shear. So that's really, that was a peer review we were doing. And AutoCAD has spell check. I tell our engineers it has spell check. But unfortunately, shear and shear, you can have it spell it both ways. This is a big little thing. This is an example of a drafting error that can cause a structural collapse. Our beam was moved off the column for whatever reason. Maybe there was another opening put in here. And it wound up on top of the reaction. So the 111 kip reaction wound up looking like 11 kips. And in reality, it's 155 kips. So this is the kind of carelessness that can cause big problems. Coordination with the architectural drawings. This is something I don't really go too far into because I rely on the design team in our office who's actually working on the project. But obviously, the architectural drawings have to bear some resemblance to the structural framing plans. And dimensions, slab edges, facade sections and details, column locations, etc. Now, this is an example. I did a peer review about a year ago. It was a concrete structure. It was a two-way slab framed floor. This was an edge column. The architect showed an opening right at this column. They basically disconnected the floor from the column. This would have fallen down. The structural drawings didn't have that opening. That opening wasn't there. So that's a case of a lack of coordination between the architectural drawings and the structural drawings that can result in problems. Coordination with the MEP drawings. The mechanical engineer is usually months behind the structural engineer with their design, but it's important to coordinate the locations of heavy runs of piping, large ductwork, beam web penetrations, etc. So anyhow, the ongoing challenges to maintain quality include understanding software limitations, training new engineers, working in a fast-track environment, and improving communication skills. So what I talked about today was the 6 elements of a QA program are training for those young engineers, establishing design standards, drawing standards, project delivery system, a knowledge base, and QA reviews. QA reviews serve 2 purposes. They provide a level of redundancy, a second set of eyes on the drawings, and they monitor the effectiveness of the QA program. And finally, quality assurance is most effective when it's ongoing. It's not something that happens at the end of the job. And that's it. Any questions? Yep.
How many people are currently in your firm?
We have about 50 people in our firm, about 40 engineers.
One office or?
We have 3 offices, Las Vegas, Philadelphia, and Pittsburgh.
How do you handle QA at the branch office?
Well, actually, the guy heading up our Las Vegas office was the assistant QA manager before he went out there. So he used to help out doing the QA reviews, and what they do is they'll send their drawings to us, and likewise, when we're overloaded, we've been sending our drawings out to them to do the QA reviews. So with the internet, everything, we're all linked together.
Are you full-time just doing QA?
Yeah, I'm the full-time QA manager, right.
You don't do anything but QA?
Well, no, actually, occasionally I'll jump in and help with connection design on some of the bigger projects, like that slide I was showing you with the 760 kip skewed reaction. I was working on that the other day. I thought, wait, this ain't going to work. And so I also do connection design in the office. Yes?
2 questions. One is about scheduling, and given that schedules sometimes get compressed or they're out of control of the design team, how do you coordinate the timely review and not having no reviews one week and too many reviews the next week?
Yeah, it's just a matter of prioritizing. Usually, somebody said one time, well, you should prioritize everything, look at the things that are urgent and look at the things that are important, and is it important or not? I go, everything that I do is important. So it's a matter of prioritizing what is the most urgent. And if we do get into a bind, like I said, we'll send stuff out to our Las Vegas office. And actually, we just hired a second QA manager. So now we have 2 QA managers, and he's going to be working half-time on projects and half-time doing QA. Yep, second question.
In setting up your program, did you think of the pros and cons of having a single QA manager doing the reviews versus alternating reviews, let's say project managers reviewing each other's work so they learn from each other? I can see pros and cons of both.
Yeah, well, I guess it happened so long ago. when we had only 7 engineers, Kirk Harmon, the fellow who started our company, he just hired a full-time QA manager, basically so that he could spend more time focusing on the business end of the firm, and it just sort of evolved that way. But I know a lot of other firms do exactly like what you're describing. But the one good thing about having a single QA manager is that there's a lot more to quality assurance than doing that review. Like I said, there's the training programs, there's getting information on the knowledge base, and there's training the young engineers, and I'll delegate QA reviews as needed to other people when I'm in a bind. But that's yes.
Yes, insurance companies usually ask if you have a written quality assurance program for your office, and so I assume you guys do. And my question would be, what do you suggest? How much detail you can get into for the written?
For what?
For the written quality assurance program.
Yeah, I'm not sure for I know we do get a cut in our insurance because we have a comprehensive quality assurance program. I don't know how we prove it to them. I don't know whether they come to our office unbeknownst to me and snoop around, but or maybe Kirk Harmon, the president of our company, maybe he handles that. But I know you can save money if you have a formal QA program. Yes?
I think we have this problem, but we work a lot with architects, and one day we got 6 updated backgrounds with major changes in them.
Mm-hmm.
These are the more highlights.
No. Yeah, you're right. Well, that's unfortunately, we've had jobs where architects have moved columns and they weren't discovered until construction. That's reckless. That's reckless. And things like that, those are the nightmares that we hear about. And of course, there was another job. The last time I gave this seminar, it was in a building that we designed, and there was a column right in the middle of the big room we were meeting in. I think they remodeled the floor since we designed the original structure. But that's a big problem, because what they do is when you call them on it, they say, well, you have the latest drawings, as if they expect you to go through 500 plans to find the mistakes. It's all about communication, like I said in the beginning. And they're having the same problems as we have in the engineering profession. They have young architects working on projects.
We produced a lot of these problems for them and for us as engineers as well.
Mm-hmm.
All days I used to get a clean background from the architect on a Mylar, and everybody worked with that.
Mm-hmm.
I don't get that anymore. And they have the same drafting problems as we do.
Yeah.
You got CAD operators who don't understand.
Right. And like I said, design used to be linear. Now you go ahead and then you have to step back and pick up revisions as the architect catches up. So it's an ongoing challenge.
One of the advantages of CAD, though, is because they do this, they said, guess what we changed? Is you can't overlay drawings, which you couldn't do with manual drafting.
Right.
And they can find these things.
Right.
They're still annoying.
Right.
But
At least you see them. Yeah.
the other problem is they said, well, just scale my drawings.
Right, for the slab edges, yeah. But you don't know whether that line is the face of drywall or the edge of slab or the face of you don't know what it is. Yes?
I guess 3 questions related to one separate. As percentage of your total annual revenue, what is your QA/QC program cost?
I guess my salary. So, no, I'm serious. That's probably the cost. I don't know. We got 50 employees, and so I'm paid more than the average probably. And but it's you can just do the math. 1 out of 50 people full time. It's a more experienced engineer. It's not going to be a young engineer. It's got to be, like I said, an engineer who's made lots of mistakes. And yeah.
Do you track the cost versus the savings? It's just too hard to track.
Yeah. Well, you know what? The thing is, what's the cost if you have a major screw-up? You hear about building collapses occasionally, and, I've seen a heck of a lot of stuff that I can guarantee you, structural engineers these days that are of a size that we are, 50 or more employees that don't have a formal QA program, it's like a train wreck about to happen eventually. Because especially with the increased reliance on the over-reliance on computer software, those examples I was giving you about the rigid diaphragms, that's stuff we see all the time. And there's a whole reason as to why you input the rigid diaphragm, but that's probably the biggest pain in the neck or potential problem.
The third question is, I have friends in other firms that serve the role that you serve. One of their biggest complaints is, damn it, they know I'm going to check it. I'm just convinced that they do a less quality job because they know I'm here, I'm checking.
Yeah, the guy who preceded me in this role, we pulled one of his emails out not too long ago. He wrote it back in the early 90s, basically reading everybody the Riot Act and telling them that don't expect me to catch all of your mistakes because it isn't going to happen. And like I said, redundancy is good, and I'm the redundant member, and it's not my role to wipe up after everybody and to catch all their mistakes. So we make sure they understand that they're responsible for getting their job done correctly, and we try to give them the tools to help them to do it with our knowledge base, with our drafting standards, our go-by drawings, and with our training. So they're under a lot of pressure, and so we're all working together as a team. Yes?
Is your program for sale?
No. Actually, a lot of people in the company were saying, why the heck are you giving away all of these secrets? And I don't know. It just seems to be the right thing to do. And the thing is, it's something we've been doing for a long time, and it's not rocket science. If you get that case document, if you get this, you're on your way. And if you read, I just read the Modern Steel Construction had the write-up that I wrote. Yes.
Comment out with respect to why to do it. We're all better off.
Yeah. Yeah. Right. It's better. Well, yeah, you're right. I mean, yeah, fundamentally, it's better for society if you teach everyone how to do their job better. But selfishly, people say, well, selfishly, you're giving away your trade secrets. But it's not really, like I said, it's not rocket science. And if we didn't do it, I'm sure somebody else would do it within a year or two. So we decided to get the credit for it.
Any comments on Vim or Revit or anything like that?
We're now making the transition to Revit, and it's painful, and the details take twice as long as they do in AutoCAD, and they look horrible. And I'm like the old school. I look at what we do as a form of art. And I love, when you detail a really elaborate connection and you just look at that, it really looks cool. And when you do it in Revit, it looks horrible. I mean, it's just, and eventually someday I'm sure the software is going to improve. But I'm wondering with the go-by framing plans, with Revit, you have a lot less control over what those framing plans are going to look like.
We have problems with live cuts. Sometimes if the cut moves or something,
or
something else, and lines disappear off
Right. Yeah, there's a lot of problems that we're still working through with that. We're making that transition, and we're going through the same pain as everyone else. Yes?
Do you check the computer models prepared by young engineers directly?
Do I check the models? Do I go into RAM or whatever? No. Our new QA manager, our new assistant QA manager, he's totally into that, going into the model. But and there's advantages to doing that. But I tell, my opinion is it's what's on the drawings right now that's being built. And something can be lost in translation. And we use RAM. I think that's the most popular program used to design steel frame floors. And there's problems with RAM. I don't think RAM can do hangers. It can't do sloped columns. There's a lot of little glitches. So what I do is I like looking at the drawings. Yeah. Yes, back there.
How do you, in your organization, improve communication skills?
How do I what?
How do you improve communication?
Well, with our quality assurance program, by having those checklists in the project delivery system, I was telling you, we have checklists. We also have templates for correspondence. We tell and templates for correspondence, one of the big things is what we call a do-by letter. It's a letter that we write to the architects telling them we need this, 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 and this by these dates. They generally hate that letter, but it's because we're basically putting into writing what we need and when we need it in order to meet the deadlines that they've given us. And that's one small way of helping to improve communication. Another way is, you know, I don't know, if you can free the engineer up from all the pain of actually doing the design, if you can get them proficient in design, it can free them up so that they can have more time to communicate with the architect. So I don't know, that's...
What we kind of try to do is let CAD guy communicate with CAD guy in the architect's office, project engineer communicate with, and I say, phone calls are cheap.
Right.
You got a problem, get on the horn and talk to the guy.
And as long as they're talking, yeah. The problem with a lot of engineers, they want to stay in their cubicle and just stay at that computer. But we try to pull them out of the cubicle and make those phone calls. Okay. I'll be happy to hang around if anybody has any other questions.
Thank you all for attending, and thank you so much.
Okay.